Hi students, hope you guys are doing well. This is another attempt to try to record my lecture, more in the tradition of how we learned in the classroom. So welcome to A&P Bio 351, Chapter 22, Lecture number 3. Yay! Alrighty, so I'm going to keep standing up to make sure you're showing it. What I wanted to start with first, we're going to go over these notes, and this would be notes that I would just write on the blackboard if we were there. And then just a little review on the past notes. Of course, we learned the anatomy of the lungs and the bronchial tree and how it gets smaller, macrophages in the alveoli that engulf pathogens, etc. Different types of cells in the alveolus that you find, type 1, type 2, plus the macrophages. And we also talked about Boyle's law. So this is just scratch. This is just scratch paper, just a review. And then I'll get to more formal writing with this. But with Boyle's law, if you had a set of lungs, well, actually, let's take a diaphragm. That's a diaphragm, and it's contracted. And the lungs, when it contracts, it gives more area for them to expand. Okay, they get larger. And not only do the lungs get larger, well, the in between all the ribs, you have these intercostal muscles. Right here, these intercostal muscles in between your ribs. And they contract as well. And therefore, the area that the lungs are sitting in is larger. And if you increase the volume, we know you're going to have a decrease in pressure. We know at sea level, the atmospheric pressure is 760 millimeters of mercury. And here, when it's at rest, it's also 760. But if the diaphragm has contracted and intercostal muscles have contracted, you have decreased the pressure. So now let's say it's 759. All right, so now the air, atmospheric air, is willing to come in. It's easier for it, easier to breathe, all right? Now, one thing about this, this is maybe at sea level, but if you were to climb Mount Everest, then the pressure may be 758 millimeters of mercury, okay? So therefore, if it's 759, it's hard to get that air in here. That's why people that climb Mount Everest will need oxygen, unless you're a Sherpa. If you're a Sherpa, then your red blood cells have a greater affinity for oxygen than what's found in most of the population. And they're able to climb it without oxygen. Helps that they were born and raised in Nepal. Going on. So now that it's contracted, we've increased the volume, decreased the pressure. If we were to relax the diaphragm, there it's relaxed. So it's relaxed. The rib cage, the muscles have relaxed as well. Now your lungs are smaller. So now your volume has decreased. And what does that do to the pressure? Increase it. So now let's say that the pressure inside of here is 761. Pressure out here is 760. The air is wanting to flow out. Easy squeezy. Now, another thing I wanted to tell you is in nature, things like to go from a high concentration to a low concentration. So 760 is higher than 759. So obviously it wants to go that way. The way you can always remember that, let's say that here's a big boulder on a mountain. And here you are. Okay? And here's your friend down here. You're like, hey, you want to play a joke? Not teasing, just so you tap it. And of course, this is going to roll down here really quickly, easily. You're still standing up there watching it go down to this person, your buddy. Well, this buddy is a little petrified. But anyway, luckily, the boulder stops right here. So this is a high concentration, this is a low concentration. Now let's say this guy has to get this rock back up here. Is it going to take energy? Yes. It's going to take lots of energy. So therefore, what I'm trying to say here is that this is a high concentration of something. This is a low concentration. It's going to take a lot of energy to go back up here compared to going here. So things like to flow from high to low. Okay, and that's what we're doing here with different atmospheric pressures. We also talked about Charles's law. So here's the lungs, and let's say that they took in a tidal volume of air of 500 mLs. And let's say it's 60 degrees out here. So when this air comes in here, it's heated. And what happens to heated air? It expands. All right, thermal expansion. So therefore, when it comes in, it heats to 99 degrees or what have you, then it's going to go to, or 98.6, it's going to go to 536 mLs. Okay, so that's going to take a larger volume than 500. So Charles's law also helps of the 4 gas laws that we've talked about to bring oxygen in. All right, now let's move on to Dalton's law. You should have notes hopefully printed out. If you can't print them out, you have this on a recording and you can take screenshots or what have you. All right, so Dalton's law is basically, if you think of the different gases in the air, you just add up the individual gases, and that will give you the total atmospheric pressure. So basically, it's the total atmospheric pressure equals a sum of all of the individual gases. So for example, nitrogen happens to be the most abundant gas in the atmosphere, 78.6%. The oxygen is next at 20.9%. Carbon dioxide is 0.04%. And then water vapor is 0.5%. All right. So if you add these up, you get 100%. Now, if we multiply this times 760, so 0.78 times 760, you get 597 millimeters of mercury. If you were to do, here's my blue, oxygen, 0.20 times 760, you get 159. Carbon dioxide, 0.3. And on a relatively cool, dry day, the water vapor would be 3.7 millimeters of mercury. If you add these up, guess what we get? We get 760 millimeters of mercury, okay? Remember, at sea level, that's what it was, 760. So oxygen is not the most abundant gas. Nitrogen is. What do we need for all of our metabolism, all of our reactions in our body? We need oxygen. Now, this is the composition of air, and this is what Dalton said. If you add up the different ingredients, you're going to get the total sum, which is the atmospheric pressure. This is at sea level. Now, okay, breathe in air. Now, this is the air in your lungs, the alveolar air. And in this, for nitrogen, you get 74.9%. Oxygen is 13.7%. I'm going somewhere with this, hang with me. 5.3% for carbon dioxide, 6.2% for water vapor. If you convert that, 760 times 0.75, basically, you get 569 millimeters of mercury, 104 millimeters of mercury, 40 for carbon dioxide, and 47 for water vapor. Add these up, the magical number, once again, is 760. But what I'm wanting to look at this is, yes, we got 760, 760. I hope I don't have a calculator here. I think 9, 13. Yeah, okay. But look, there's a difference here. The pressure of air for oxygen is 159, but when it comes into your lungs, it drops down to 104. Here, 0.3 carbon dioxide in the atmosphere is barely any pressure. Here we have 40 in your lungs, okay? So my question is, why is the composition of air different than the alveolar air? Why is this column different than this column? Well, if we were in class, I would hope you to kind of guess, and some of you may can go ahead and guess what it is. But the differences are caused by, think about it. When this air comes into the lungs, it comes in contact with a lot of moisture in the membranes, all right? So 0.5% to 6.2% is mixed with a lot of humidity, all right, inside the alveolar, because it's very humid and moist in there, because you have the serous fluid on the outside of the alveolar. It's a moist environment. So first of all, you can say the alveolar air is humidified, heat and moisture, by making contact with mucous membranes. So that moisture causes the water vapor to go up. Number 2, freshly inhaled air mixes with residual air. So therefore, the oxygen is diluted and CO2 is enriched. And let's look above here, okay? So if we look up here, the CO2 goes from 0.3 to 40, okay? Because think about it. Scratch paper. Here comes fresh air. Here's your lungs. You have 159 millimeters of mercury of air coming in, of oxygen, excuse me. All right, but what's down here already are your alveoli, and we want a lot of oxygen to go in here, and as soon as it comes down the conducting zone, it's mixing with a lot of CO2 that's on its way out. All right, so this mixing process causes a difference between the oxygen and the carbon dioxide. And also, as soon as it comes in, it starts going through gas exchange. So the last one, alveolar air goes through gas exchange. All right. Okay, so that's good enough. All right. So moving on. Now let's look at Henry's law. Now let me just tell you what Henry's law states. Henry's law. At the air-water interface, the amount of gas that will dissolve into the water is decided upon by the solubility of the gas in the water and the partial pressure. So how can we say this easily? So when I say that air, so here's the alveoli. Here's an alveolus, okay? So what Henry's law says is, as, for an example, the oxygen come in, how well it can cross the membrane, the air-water interface, depends on how soluble the oxygen is into the membrane and its partial pressure. So we know when its partial pressure, when it first comes in, is 190. But once it's in here and all the mixing and all the 3 reasons we just talked about, it comes down to 104. So we can see that right here, 104. So Henry's law basically says, once again, this is the air-water interface. How well the oxygen crosses this interface depends on its solubility and partial pressure. And when I say partial pressure, it's basically the partial pressure of the whole atmosphere that's oxygen, okay? So, make sure I'm on, right, okay. So now, let's just put this in words. At the air-water interface, boy, I hope you can see this. For a given temperature, I threw this in there. Basically, it can change with the temperature, but we're saying at a fixed temperature, the air-water interface, the amount of gas that dissolves in water in the membrane depends on its solubility and pressure. Okay. All right. Any questions? Oh, okay. I hope not. Well, I mean, I hope so. Well, I can't answer them. So you can ask me tomorrow at 9:30 when we actually meet live. Tuesday, tomorrow. All right. Hopefully you can still see this. Hopefully you can make it bigger. Let's see if I can make it bigger. Ooh, I can, but I probably messed it up. I don't know. I'll make this one bigger, and I'll slide this over a little bit just to see. This might be messing me up. I don't think I can made it too big. Maybe I'll make it a bit smaller. Haha. All right, so what's going on here? Okay, let's focus on this picture here. You should have this in your notes. Okay, you've just brought in some air all the way down. This is 1 alveolus. The partial pressure of oxygen is 104. Look back up at the top and you see that that's what you have once it's in the alveolus. The CO2 is 40. Okay, this is a capillary lacing around the alveolus. And coming into the capillary, we have blood that is low in oxygen. So the pulmonary artery is bringing the blood to this eventually to this capillary, and its pulmonary artery is very low in oxygen. All right, so we can look. So the oxygen is 40 millimeters of mercury, and the carbon dioxide is 46. Okay, so it's a little high in carbon dioxide, and it's low in oxygen. As this comes around, as these capillaries are laced all around the alveolus, we know the pressure inside of here. So if it's 104 millimeters of mercury inside the alveolus, and this blood just coming through here is 40 millimeters of mercury of oxygen, just like the rock that I showed you, it's easier to go to 104 to 40. So naturally from high to low concentration, the oxygen is going to diffuse over, all right? If this is 46 and this is 40 for carbon dioxide, the carbon dioxide is going to diffuse out into the alveoli. Now, once this exchange happens, this gas exchange, we look up here and see what the results, what's happened. We now see that oxygen has increased to 95. Down here it was 40. The carbon dioxide has decreased to 40, all right, and it was 46. So now this is oxygen-rich blood. It's going to flow back through the pulmonary vein to the heart, make it to the left ventricle, to the aorta, and it's going to take this oxygen-rich blood all to your body tissues. All right, so let's follow this blood. Okay, let me just use red. So yeah, we have oxygen-rich blood, and it's coming, all right? O2 rich, okay? Comes down here, and now the blood flow, here we have the oxygen-rich blood, and it's low in CO2, okay? It's only 40 millimeters mercury of CO2. Now, I've probably gone off screen, so I pull it down, and here we go. Now, you just got this oxygen. These are tissue cells, all right? Our whole goal is to bring the oxygen to the tissue cells all over the body, okay? And so we know that right here, this blood that we're bringing is 95 millimeters of mercury of oxygen. See, over here, I'll make it was over here was 95. And what was the CO2? The CO2, look over here, was 40. All right. Now, right now over here, in the tissue, since we've used up the oxygen in metabolism and we got a waste product of carbon dioxide, over here, the oxygen is 40 and we're high in carbon dioxide at 46. Look, here's 95, here's 40. The oxygen wants to come across, okay? The oxygen wants to come across. The CO2 wants to get out, all right? So, great, they have gas exchange. Now, this blood right here has to head back to the lungs, okay? It's a cycle. So now, once this gas exchange happens, the blood is 40 millimeters mercury of oxygen, and CO2 is 46. So now let's follow this blood right here. Going. It's going. All right. And we do it over again. So this, Henry's law, depends on the partial pressures of which way the gases will go. So hopefully this made sense, and we'll move on.